Hey everyone, and welcome to this explainer. Today, we're going to take one of the most famous and, frankly, counterintuitive concepts in theoretical physics and watch it come to life in a real, tangible laboratory setup. We're talking about Bernoulli's theorem. If you've ever wondered how engineers actually prove the math that keeps massive airplanes in the sky or water flowing perfectly through our cities, well, you're in the right place. We're going to break down the specific equipment, the FM24 demonstration unit, that turns those abstract equations into hard, visible data. Let's get right into it.
Now, I want you to picture this for a second. What actually happens to pressure when a fluid speeds up? Your intuition probably screams that as a fluid gets squeezed into a tighter space and accelerates, the pressure just has to go up, right? Kind of like clamping your thumb over a garden hose. But that is the beautiful, paradoxical nature of Bernoulli's principle. In a steady flow of an ideal fluid, as the velocity increases, the static pressure actually drops. I know, it feels completely backwards. So today, we're going to look at the exact machine designed to prove this paradox is an absolute reality.
Here's our roadmap for today. We'll cover the Bernoulli paradox, the FM24 demonstration unit, the anatomy of the setup, priming the system, running the experiment, and finally, the reality of friction.
Let's kick things off with Section 1, the Bernoulli paradox, moving fluids and shifting pressures.
All right, so here's the legendary formula, translated into simple terms. Bernoulli's equation essentially dictates that in an ideal, completely frictionless fluid, the total energy remains constant. This total head is made up of three distinct parts: the pressure head, the velocity head, and the elevation head. Now, because our lab equipment is set up on a flat, horizontal plane, the elevation head, that z value, is totally zeroed out. So we're basically looking at a balancing act between pressure and velocity. If velocity goes up, pressure simply has to go down to maintain that constant total head. It's the conservation of energy visually mapped out right there in a continuous stream.
Moving on to Section 2, the FM24 demonstration unit, hardware for the hypothesis.
Okay, let's dive into this setup. What you're looking at is the FM24 Bernoulli's theorem demonstration unit. It's honestly a beautifully engineered piece of hardware. The whole apparatus rests on a flat baseboard, perfectly leveled on top of a hydraulic bench. You can spot the transparent test section at the bottom where the water flows, and right above it, this towering board of manometer tubes. This is where the magic happens, folks. Those tubes are going to act as our live barometers, visually displaying the shifting pressure of the water as it moves through the varying widths of the pipe below.
And this brilliantly illustrates exactly what's going on inside that pipe. You can see the fluid's path, right? It enters a converging section where the pipe narrows, passes through the tightest point, which we call the throat, and then enters a diverging section where it opens back up. The centrifugal pump draws water from the reservoir, and as it hits that narrow throat, the area decreases so the velocity hits its absolute maximum. And according to our theory, this is exactly where pressure should be at its minimum. The varying water levels you see in the schematic's vertical manometer tubes show exactly that, a crazy dip in pressure at the throat, followed by a rise as the pipe widens again.
Next up, Section 3, Anatomy of the Setup, Component Breakdown.
So this machine is built to incredibly exacting specifications. Let's do a quick teardown of the core specs. The Venturi, that transparent acrylic pipe we were just looking at, narrows down from an upstream diameter of 26 millimeters to a tight throat of just 16 millimeters. It easily handles a designed flow rate of 20 liters per minute, and that's powered by a massive 120-liter sump tank hidden in the hydraulic bench. And what about those 8 manometer tubes? Well, they each stand 320 millimeters tall, basically standing by to capture the static pressure and total head along the entire length of the Venturi meter.
Now, this is one of the most clever components of the entire setup for sure, the hypodermic probe. Unlike normal pressure taps that just sit flush against the pipe wall, this probe can gently slide horizontally right along the inside of the Venturi tube. When the fluid hits the tip of this probe, it's forced to a complete dead stop, zero velocity. By stopping the fluid in its tracks, the probe captures the combined power of both the static pressure and the kinetic energy of that moving fluid. And this gives us what we call the total stagnation head.
Another tiny but absolutely mighty component is the air bleed screw, located right up on the manometer board. If you've got air bubbles trapped in your water lines, your pressure readings are going to be entirely compromised. So this small valve allows lab technicians to safely release trapped air and adjust the pressurization of the tubes. If the water levels are sitting way too high or just out of a visible range, this little screw is exactly how you tweak the static pressure to bring those readings back into view.
All right, Section 4, priming the system, bringing the machine to life.
Now this is where theory meets practical, wet, splashy reality.
First up, the baseboard absolutely must be perfectly leveled using a spirit level and its adjustable feet. If it's not, gravity is going to skew our pressure heads, and we definitely don't want that. Next, we fill the volumetric tank to about 90% capacity. Then, with the pump switched on, we gradually open the flow control valve to let those pipes fill up. Finally, we execute the most crucial step, gently pressing that air bleed valve. The manual literally warns you to take care here or you're going to drench yourself or the lab. You really have to allow a sufficient time for every single trapped bubble to escape the system to ensure maximum accuracy.
On to Section 5, running the experiment, capturing the data. If you were actually standing right there in the lab, this is the exact results matrix you'd be filling out. You take readings at different cross-sections, labeled A, B, C, and so on, with C being that super narrow 16mm throat. For every single cross-section, you measure the total head and the static head. Then, the real test begins. You calculate the velocity based on Bernoulis' theory using those pressure differences, and then you calculate the expected velocity based on the pure volume of water flowing through the area. That's the continuity equation. The final column, the difference, well, that's the moment of truth, where you see if reality actually aligns with the math.
So, the crucial point is how we actually get those two initial numbers for the matrix. When you slide the hypodermic tube over to cross-section A, it connects directly to manometer G. Because it forces the fluid to a stop, manometer G gives us the total stagnation head. Meanwhile, manometer A is connected straight to the wall tap at that exact same cross-section, which doesn't obstruct the flow at all, giving us pure static pressure head. By simply calculating the difference between manometer G and manometer A, you perfectly isolate the velocity head. It is just an incredibly elegant mechanical solution to capture an entirely invisible force.
Finally, Section 6, the reality of friction, head loss in the real world. Let's move on and see how this builds a much more complete picture of fluid mechanics. You see, Bernoulli's equation assumes an ideal fluid, one that is completely frictionless, perfectly steady, with a perfectly constant total head. But out in the real world, water flowing through our acrylic Venturi tube experiences friction against the pipe boundaries. The fluid velocity just isn't totally uniform across the pipe, and there are real losses of energy as the water churns and creates turbulence. The total head doesn't stay perfectly constant. Some of that energy is permanently lost to the environment as heat and vibration.
Experimental analysis of this exact Bernoulli setup has allowed researchers to track down exactly where that lost energy goes. According to studies of this apparatus, about 66%, or a solid 2/3 of the lost energy, is due to minor losses associated with the fluid being forced into the converging section and then expanding into the diverging section. About 10% is purely friction loss against the pipe walls, and the remaining 24%? That's eaten up by turbulence effects, piezometer fitting losses, and the chaotic setup of the flow itself. It really shows us that to apply Bernoulli's principle in the real world, we absolutely must always account for a head loss variable.
Which leaves us with this final provocative thought. We've seen how meticulously we have to measure and adjust for friction in just a tiny 16mm acrylic pipe in a perfectly controlled lab. So friction and turbulence always alter the results. How do engineers scale this up? How in the world do they design massive, real-world, citywide infrastructure, water mains spanning for miles, jet engines, sprawling oil pipelines, that perfectly balance pressure and flow despite all these messy real-world variables? Well, it all starts right here, with understanding the baseline of Bernoulli's paradox and mastering the complex reality of friction. Thanks so much for joining me on this explainer, and I really hope you walk away seeing the invisible forces all around you just a little bit more clearly.